We've just heard about a large number of threats that internet voting systems would have to deal with. Most of these are problems that other kinds of online systems are subjected to all the time. But with experience with real internet voting systems, the few that have been deployed in practice, we seldom hear about attacks against them. And this could just be because attackers who really do break into a system very rarely will admit in public that they've broken the law and successfully stolen votes. But what I'm about to tell you is going to be the best experience we have with the security of a real deployed internet voting system from people who hacked into it and are able to tell about it. And what I'm about to tell you is the story of how I hacked into the Washington, D.C. internet voting system. In 2010, the District of Columbia, essentially the city government of Washington, D.C., announced that they were going to implement a new pilot system for allowing absentee voters living overseas to cast their ballots over the internet. Now, when D.C. announced this, they did some things right. One thing they did was they went to the research community and asked people who study electronic voting how they should build their internet voting system. And what most researchers told them was the same. They said, no, don't do internet voting. The technology is not mature enough. There are going to be too many risks. But the D.C. officials decided to go forward with their pilot system anyway, and they scheduled it for use in the 2010 general election. One thing they did that was perhaps a compromise with the research community was the D.C. officials announced that they were going to hold a public trial where anyone interested would be allowed to try to hack into the system during a mock election that would be held just before the real election and prove that there were problems with it. So in general, this kind of pilot study and this kind of adversarial test has a few problems. First, these pilot studies usually have very unclear goals and criteria. And as a result, the people who run them almost always declare that they're successful when they're done. Second, they usually have unrealistic ground rules for testing, limitations that a real attacker wouldn't face. Very limited time to prepare, for instance, limited access to the system. All of these things make it harder to demonstrate flaws as a researcher without making the system any more secure against real attackers. Finally, if no problem is found, that doesn't necessarily mean there are no problems. It could just mean that no one was interested in testing it, or that the people who were testing it weren't very good or weren't very lucky. A real attacker, we always want to assume in security, is going to be luckier, more resourceful, and smarter than we are. Despite these problems, the D.C. offer of a public test was just too good to pass up. It's not every day that you're invited to hack into government computers without going to jail. And anyway, this was going to be one of the best chances we'd have as a research community to see how election officials might respond in the event of a successful attack if we were to get in. There were still some big problems with the way the D.C. test was set up. There were only a few days notice given before the mock election was going to start, and it stopped just a few days before real voters had to use the system. Not nearly enough time to fix any problems that might be found. Furthermore, we could only test the server side of the system. The client, and demonstrating attacks like adding malware to people's PCs, would be off limits, since we couldn't actually break into other people's home computers to test that out. Still, as I say, this was too good an opportunity to pass up. And so my research team at Michigan and I took part in the D.C. trial. So let me start by telling you a little bit about how their system was designed. It had a lot of very nice security features. The system ran on a series of servers in Washington that were well isolated from each other. There was a firewall in front of a web server and another firewall in front of an application server that ran the actual vote counting software. That software was written in a programming system called Ruby on Rails that is really widely used for developing other kinds of online services. It was developed by a team of volunteers who were experienced web developers, and they even made the software open source so that other people could evaluate its quality. So let me walk you through the DC system as a voter would use it. The voter would first go to the homepage of the election and declare that they wanted to vote a digital ballot. The system also had a way to just download a blank ballot, fill it out, pencil and paper, and mail it back. But the path we're concerned with is the digital voting, where you send your vote back over the internet. So the voter would then see this user-friendly screen outlining the process, and then they'd authenticate to the system. They'd fill in their name and voter ID number, as well as a long alphanumeric PIN number. This would be a PIN sent to the voter in the mail along with their instructions. And by the time the mock election took place, all the real voters who were going to use the system had already received instructions and PINs. At this point, the voter confirms their identity, and then they're given the option to download a ballot. Now, the ballots in this system were PDF files, and part of the reason for this was that the election officials at the end of the process were going to print out these completed ballots and count them along with other vote-by-mail ballots. So the voter uses their PDF reader to mark their preferred candidates and saves the PDF file, then goes back to the website, uploads the saved file. That's it. The ballot is cast. The voter sees a thank you screen on which they can then tell everyone they voted on Facebook and Twitter. So now you've seen how this works, why don't you think a little bit like an attacker and try to figure out what mechanisms you might use to try to attack the election server in the DC system. Then I'll tell you what we came up with at Michigan when we come back. Let me tell you about my approach to attacking the DC system. In looking at the system, I tried to, as closely as I could, play the role of a real attacker and try to do the things a real attacker would. The first thing I did was I recruited a really good team of technical people to help me out. And these included my students, Scott Walchuk and Eric Woostrow, as well as Dawn Isabel, a member of the university's technical staff who holds the most awesome job title in the world of ethical hacker. Her job is to help the university with its own internal security testing. So with this team assembled, we started looking at the DC system from the safety of our laboratory, not wanting to let on that we were attempting to penetrate it or that we were even interested. So we downloaded a copy of the source code. And DC did a great thing by making this open source because, for one thing, it made the test much more realistic. In a closed source system where the code isn't available, resourceful attackers are probably going to be able to find it anyway. How could they do this? They could bribe or coerce some of the developers involved. They could break into some of the developers' computers. One of the attacks against Google I mentioned in the last segment was an attempt to steal some of Google's source code. All of these things would be off limits in a penetration test like this. So making the code available to the attackers at the beginning just helped to make it a realistic simulation. So when we looked at the code, we spent probably 4 or 5 hours reading through it. And I tried to apply the security mindset and think like an attacker as much as possible in this process. So we concentrated our efforts on places in the code that are on what's called the attack surface. That is, things that an attacker might be able to cause to run, things that process data that could be controlled by an attacker, and so forth. These are going to be the easiest parts to exploit if there's any kind of mistake the programmers have made. So after a few hours of looking at the code, we finally homed in on this procedure. And probably most of you aren't going to know what's going on, but some people who understand Ruby on Rails will get a sense for it. The yellow line there caught my eye. What's happening here is that this is part of the code that processes ballot files after voters upload them. And the server is programmed to store the uploaded ballot in a temporary file and then run a command to encrypt that uploaded ballot. The ballots would be encrypted with a public key, the corresponding private key to which was stored offline. This was meant as a way to help boost ballot secrecy, so that anyone who did access the server wouldn't be able to read the ballots. They could only later be read after being moved to another computer. But in the process of doing this, the programmers made a mistake. So if you look at this line, this is the line that's causing the ballots to be encrypted. There's one subtle glitch. They've used double quotation marks in a place where they should have been using single quotation marks. This turned out to be enough to completely compromise the system and steal all the votes. So let me explain what's happening here a little bit better. When I upload a ballot, it gets stored into a temporary file. If the ballot is named ballot.pdf, the temporary file is going to be some random name .pdf. But we noticed that because of a glitch in the code, if I named the ballot ballot.xyz, the temporary file would also be named something.xyz. That piece of the file that's called the file extension, that normally tells you what type of file it is, ended up being used without any changes on the server. Now, the problem is that this kind of processing that the server was doing to encrypt the file was essentially just something that would be executed on the Linux command line on the server. It was forming a longer command involving the file name and then telling the computer to run that command. So if we took another command, let's say a command that says sleep 5, which tells the computer to just pause for 5 seconds, and put that in a certain formatted way into the name of the ballot file, that would appear verbatim on the server and be executed as part of the command that the server ran to encrypt the file. Because they used double quotation marks in a place they should have used single quotation marks, the server doesn't just treat whatever's uploaded as a name, it will treat it as a name that might have other commands embedded in it. So this little glitch, a small punctuation error, coupled with a problem of not sanitizing that file extension, was enough to take over the server. Even though we thought we'd have a way into the system thanks to this vulnerability, we didn't know for sure whether this would actually work on the real election server the way it was really configured. So far, we just were speculating about it in the lab from reading the code. And so we spent a lot of time doing other surveillance on the network, scanning the set of network addresses that the DC officials announced were part of the test, to see what else was plugged in and whether there would be any other avenues for an attack if we needed a plan B. So we mapped out the network and how everything seemed to be connected. And we found one very interesting device plugged in. This was something called a terminal server. This is a device that network administrators use to gain remote access and do setup and configuration tasks on other pieces of network plumbing. So this is all happening much lower in the network, in the pipes, so to speak. What we found when we looked at the terminal server was it told us what model it was when we connected. And we were able to Google and find the owner's manual on the manufacturer's website. It told us that these devices shipped with a certain default password installed. So we thought, let's try that. Turns out the people who set up this device never bothered to change the default password. Well, it's an easy mistake to make. But what it let us do was take over the terminal server and change its programming to add a certain kind of backdoor that would let us see in real time as the network administrators logged into and configured the other pieces of their network plumbing, including some very high-end routers and switches that were going to be used elsewhere on the DC network. We were able to get all of their passwords when they logged into these devices, to watch what programming changes they made, and potentially that would have given us a way to reprogram those devices in the real election. But there was one other thing we noticed when we were hacking into the terminal server, and that's that we weren't the only people trying to attack it. The other attack attempts, I'm convinced, were not at all part of the authorized DC trial. Instead, they were intrusion attempts coming from real attackers in Iran and in China. Now, I don't think that these attackers were actually targeting the Washington DC voting system. I think they had no idea what they were trying to hack into. These were probably automated attacks that are an everyday phenomenon all across the internet. There are attackers who are just trying to hack into whatever computers are vulnerable in order to add them to their botnets or use them for other criminal purposes. However, we didn't want that to interfere with the DC trial, and it would have been very easy for them to eventually guess the default password on this device. So we did DC a favor, and we changed the password to something stronger to lock out those real attackers. Even though they probably weren't targeting the election, it's an important reminder of the kinds of global hacking threats that an internet voting system has to overcome. So at this point, we had real-time views into the configuration that was being done on the network by the real sysadmins. We also found something else really revealing on the network, and that was a series of network cameras that had no password whatsoever, but were broadcasting real-time views of the server room. We got to see the server hardware where the election was going to take place, and we got to watch people coming in and out of the data center. So we could see if they were making any system changes, for instance. We could also see some of their security procedures. Here's the night watchman who can't tell that we've hacked into the systems. Also, this gave us an incredible amount of perspective into whether our other attacking attempts had been caught. We could tell by the change in the attitude and look of the system administrators between before and after they eventually learned of our intrusion. So before, they were quite calm. Afterwards, they seemed pretty upset. At this point, our preparations were complete. It was time to try out our attack against the real server. We decided to wait until after 5 o'clock because we could tell from the security cameras that that's when the people monitoring the system usually went home for the night. After 5, we logged into the web server and tried to upload a ballot containing malicious commands that would exploit the vulnerability we had found in the software. To our surprise, it didn't work. There was a glitch. It turned out that we hadn't anticipated one part of the configuration. So we had to do some more engineering back at the drawing board, back in the lab. After some heroic effort by my students, by 9 p.m., we finally were in. We had complete control of the server. Now, I want to pause for a second and let you think about what you would do in this situation. So you're playing the role of an attacker. What are you going to do to the server now that you have control? So here's what we did after we had broken into the DC Internet Voting server. The first thing, like a real attacker would probably do, is we stole everything we could. That is, we collected the database passwords, keys, log files, any data that might possibly be useful for us to break back into the server in case the election officials caught on midway and tried to kick us off. The next thing was we launched the main payload of the attack. We changed all the existing votes to be votes for our own slate of candidates. And here's the ballot we voted. Every race has a write-in candidate for an evil robot or AI from science fiction or the movies. Notice Bender from Futurama for school board. So the votes were encrypted until it was going to be time to count them. And because of this, there'd be no way for the election officials to notice that we had changed the votes until after the election was over. The encryption, however, didn't present any obstacle to us because the votes were being encrypted with a public key that was on the same computer. Next, we rigged the system to replace any subsequent votes with our slate of evil robots. This involved changing the software running on the machine to make it dishonest. After that, we added a backdoor, something that would compromise ballot secrecy and allow us to figure out how everyone intended to vote. Even though their candidates were being replaced with our candidates, we would still know what their original intent was, violating the secret ballot. Like a real attacker, the last thing we did was we cleared the logs and tried to erase all the evidence that we had broken into the system. But still, part of our exercise was to try to test how well election officials would respond. Would they be able to detect the attack and recover from it? So we decided to give the election officials a little bit of a leg up, and we left a kind of calling card for them. What we did was we changed the code on that thank you page that appears every time a voter completes the process. We added these lines. After a delay of a few seconds, the voter's PC will start playing The Victors, the University of Michigan football fight song. Even though we had added the fight song to the page every voter would see, it still took 2 days before election officials noticed. And even then, it was only because another person testing the system wrote an email to the DC officials saying, everything looks pretty good, but I don't like the music that plays at the end. It's too distracting. There was one more thing that we found in the system, this was probably the most disturbing thing of all. In the directory where the uploaded ballots were stored, there was another glitch in the system that prevented the temporary ballot files from being erased when they were done. And we noticed that there were a bunch of files left over that people had uploaded in testing the system even before the public trial began. Someone, an insider at the election office, had been testing it and had been making sure it rejected files that weren't proper ballots. It looks like this person just uploaded files that were lying around on his PC at the election office. The installation files for a software program, for example. But one of the files was much larger than the others that had been used in testing. This file was a 937-page PDF document. When I opened it up, I couldn't believe what I was looking at. Every page looked like this. This file was the actual mail merge for the letters sent to the real voters, including the secret PIN for every real voter invited to participate in the system. These letters had already been sent out. There wasn't time before the election to send out another round. And the officials had, through very, very sloppy testing, given away the passwords for all the real voters on a server that they invited the world to hack into. There was no way that the real election could be securely performed now that these credentials had been given away. So in the wake of our attack, Washington, D.C. officials evaluated again whether they wanted to use the system and, in my opinion, very correctly decided not to use it with real voters in the actual election. Instead, they did something that is very sensible. They made the path to let voters download and print a ballot and mail it back available to all the real overseas voters. This provides far fewer security risks than actually collecting the votes on a server that could be hacked into. So there are a number of lessons that I draw from the DC experience. One is that web applications tend to be brittle. Small mistakes, like those double quotes instead of single quotes, can have huge consequences, like all the votes being stolen. This is an inherent problem with the way web applications are developed today. The technology just is not secure or mature enough for applications like voting. Another problem is that officials are just not very well equipped to detect and respond to server-side intrusion. It's hard enough for Google, the Pentagon, security companies. Election officials at jurisdictions around the world have far fewer resources. One of the biggest problems with internet voting is that a lot of the threats that stand in its way are some of the biggest challenges in computer security today. Problems like phishing, problems like people breaking into servers, problems like malware on clients. These are things that everyone wants to solve for every other online application. And it's extremely unlikely that we'll find a way to make all of those problems go away just for voting without years and years of research to try to improve the state of computer security across the rest of the internet. For this reason, my conclusion is that it's going to be decades, if ever, before we're able to vote online securely.